Swayam Prabha. Digital India. Educated India.
Welcome to the final lecture on wetting on rough and textured surfaces. In the previous couple of lectures, I've discussed the relevance of the rough surfaces in many natural and industrial settings. Then we analyzed the problem of roughness, the absence of roughness, how when you have a smooth surface, what's the contact angle that we get. We've already done this in various ways in the past, but I've also repeated the analysis for an axisymmetric geometry. And as expected, we recover the Young's contact angle even in this geometry. Further, any external field that is present in the problem, such as let's say a gravitational field, does not affect the boundary condition at the contact line. And we extended this to this approach to consider to textured surfaces. We have a controlled roughness elements, where in the first case we have a textured surface which is called the Young Wenzel state. The liquid basically completely wets the solid surface, and the liquid penetrates into the roughness elements. And we did a detailed theory for this case. And then we looked at the Casey-Baxter state, where there are chemical heterogeneities. The contact angle, the apparent contact angle that one sees, depends on the Young's angle on each of these individual roughness elements and the area fraction that is occupied by these chemically heterogeneous elements. They're not necessarily roughness elements, they're chemically heterogeneous elements. And finally, the third case which we have to look at is the case where the droplet is actually supported on tiny pillars, and between the droplet and the pillars air is entrapped, and that's the case what we're looking at in today's lecture. I have to mention that there are many more combinations that are possible. For example, we could have a combination of chemically heterogeneous surface along with either Casey or the Casey-Baxter state, where we have undulations on the surface. We could also have a curved surface. The curvature of the surface is completely ignored in this analysis. Another possibility is that the roughness elements are not so simple as we've seen here, but they could be hierarchical structures, and so on. So the area of wetting on rough surfaces is an active area of research, and therefore any list that I make will certainly fall short of our current understanding of the problem. The analysis for the Wenzel state was very similar to the analysis for the rough case, for the smooth case, where we obtained the Young's law. The only difference is that the energy term, which takes into account the interaction between the liquid and the solid, that energy term now has the roughness parameter R, because there is an excess surface area, and this excess surface area is modeled with this roughness parameter R. You may recall that this roughness parameter R is nothing but the ratio of the actual surface roughness of the actual surface area of the rough surface to the projected surface area. Now we continued the same discussion for applied the same idea even for surface with chemical heterogeneities, but now we need to also take into account the fact that the surface energies themselves can be different at different parts of the surface, and therefore that goes into the energy functional. And when the drop is basically sitting on the surface, on the smooth surface, we also have to take into account what percentage of the area is covered by a certain type of chemical heterogeneity. that's modeled with phi s, where the subscript I represents the superscript I in this analysis represents the number of such area, the chemical heterogeneities that are present in the system. For example, if you consider a simple situation where there are only two chemical heterogeneities, and the example that I gave was a case where we have a smooth, clean glass surface, and along with the same surface etched or chemically treated at a few places on the surface using various techniques like masking. Now, what we have is we have a smooth surface but different chemical properties on the surface, and these different chemical properties lead to a complex interface angle at the wall, and that's the apparent contact angle that we can determine once we know what percentage of the surface is covered with these treated regions and what percentage of the surface is treated with untreated regions. So F1 and F2, they are basically a shorthand notation for these phi S1 and phi S2. So these F1 and F2 are basically the corresponding regions of surfaces with different chemical properties. So now we want to conclude this discussion using the Casey-Baxter model with air pockets in the middle, and that's where we will start this lecture. So let me first begin by highlighting a region, small region, let's say a region very close to the solid surface. So roughness element would be something like this. These are the roughness elements, and the droplet is approximately flat in the middle. This need not be the case, but that's the simplistic model that we have taken. And once we do this, we can now say that this is solid and solid, and the entire region above is the liquid. That's the liquid region, and we have air here, air in these regions, right? So we can come up with a very simple strategy to get the answer rather than working out a detailed analysis. So if we look at the previous case, we were able to get the apparent contact angle in terms of area fractions of different types of surfaces that makes up the composite surface. So from the previous analysis, on a chemically heterogeneous surface, we have cosine of theta star will be F1 cosine of theta 1 plus F2 cosine of theta 2, right? This is what we have. Now what we can do is we can simply say F1, let's call it as phi s, and this is nothing but the relative fraction of the solid islands, or the upper surface of the pillars. In other words, I'm highlighting these regions here. That's the size of the pillars, the area of that is occupied by the pillars that I'm highlighting in yellow, and that's F1, and theta 1 is contact angle at the solid, which is same as the theta y. On the smooth solid, if the contact angle is theta y, F2 is nothing but 1 minus phi s, because if I take the entire surface, if the fraction of the surface which is occupied by these pillars is phi s, then the rest of it has to be air pockets. So this is the width of the air pockets. This is relative fraction of the air pockets. And in this case, theta 2, the angle at this, for this air pockets, you can simply say it is 9, it is it is this is the angle that the interface makes with the air pocket, which is basically 180 degrees. Why? Because if you notice here, the interface is smoothly merging with this with the flat interface on top of the air pockets. If I just use these expressions, then I simply get cosine of theta star will be f1, that becomes phi s, cosine of theta y, plus f2, that is 1 minus phi s cosine of pi. That is nothing but phi s cosine of theta y minus of 1 plus phi s. And I simply get cosine of theta star is minus 1 plus phi s times cosine of theta y plus 1. This is the Casey-Baxter model with air pockets. Right? Now, there are some nuances to be mentioned here. The actual application of the principle of virtual work, or the minimization, the variation principle that we had used, is actually a little tricky in this particular example. The primary reason for this is that if you notice, if you look at this, the interface shape, and where the interface meets a solid, you can certainly have the interface coming and meeting the solid on top of a pillar, but the interface cannot actually come and meet the substrate between the air pockets, right? So clearly the interface cannot be supported between the air pockets, but the interface can be supported on top of the pillar, and therefore a straightforward application of this variational principles is at least problematic in this sense, that we can't basically just consider a simple circular contact line when viewed from the top. We have to reconcile that the contact line will actually meander a bit. Why would it meander? For example, if you look at the from the top, if I look at tiny pillars as follows, if these are the position of the pillars, I'm just drawing some random pillars. The or these are the contact line has to meander around these pillars where it meets the solid. Okay. Now these, either they could be these little circles that I've drawn could be tiny holes on the surface where the contact line certainly cannot be at that location, or it could be it could be tiny beads that are placed on top of the surface. So in such a case, if you actually look at it macroscopically, it may appear like a smooth contact line, but if you actually zoom into the region near the contact line, then the contact line will certainly meander. The contact line position will certainly will not be smooth, and this meandering that you see here will give rise to an excess free energy of the droplet, and you can relate it to the so-called line tension and elasticity of the contact line. But those are all ideas that would take us too far away and too deep into this topic of wetting on complex surfaces. So therefore, I would urge interested students to look at this topic you will find this discussion in various research papers. So what I now want to do is to basically look at another important extension of this by looking at the case where we have a flat surface and we have a local analysis that we've done. This kind of a local analysis was done when we did the analysis for the Young's angle, but we did not do this kind of a local analysis for the Cassie and the Cassie-Baxter and the Wenzel states. So let's quickly look at this local analysis. The local analysis also gives us some insights and it will help us understand the wetting transitions. For example, on the left side, what you see is the Wenzel state, because the contact line, the fluid completely wets a solid, and the other hand, you have the Cassie-Baxter state. In both these cases, what we want to do is, we want to consider a situation where the contact line has moved by a distance of dx, and we want to find out what is the change in the energy in this process. So remember that the Wenzel state completely impregnates the fluid. Let's do the analysis first for the Wenzel state. For the Wenzel state, the change in the energy associated, let me write that down, change in the energy associated with a fluid front moving a distance dx. In this case, if it moves a distance dx, we have to recognize that when we move a distance dx, we have created a new surface which is dx cosine of theta star. So the change in the energy, we'll call it as dEw, where the subscript w represents that we are writing this for a Wenzel state. This quantity would be gamma times, or rather, sorry, the roughness element times, we have increased the roughness on the surface, therefore it will be gamma SL minus gamma S dx. When r is equal to 1, we would get the case for a smooth surface, but now we have increased the surface area, therefore the effective increase in the surface area would be r times dx. That's what goes into the discussion, into the expression. And finally we have gamma cos theta star dx. That's the dx, the cosine of theta star is the excess surface area that we've created. So let me mention that if r is equal to 1, we have a smooth surface and we get the Young's law. That's the case for Young's law. Now if we set dEw is equal to 0, then we get cosine of theta star will be r cosine of theta e. This is exactly what we got from the variational approach as well. And in other words, wetting tends to amplify, the wetting tendencies get amplified with roughening. A hydrophilic surface becomes more hydrophilic. A hydrophobic surface becomes more hydrophobic. Okay. Now, the next obvious question is, what happens at large r? So when r is much larger than 1, Wenzel state can break down. Clearly, mathematically, that should be fairly evident. When r becomes much larger than 1, you may reach a situation where cosine of theta star can exceed 1, which is physically impossible. And what will end up happening in physically is that the Wenzel state basically completely breaks down. And in this case, when r becomes very large, which means that the roughness has increased quite a bit, then fluid does not anymore penetrate the all the depths of the roughness, and you would start trapping air pockets. In this case, what tends to happen is air gets trapped within the roughness elements, and then the Casey-Baxter state emerges. So we have at least one way to look at the transition from the Wenzel state to the Casey-Baxter state when R becomes very, very large. What about the other case of the Casey-Baxter state? Let's do the same kind of analysis. We have moved the interface by a distance dx, and this leads to creating an excess area on the interface, that is the liquid gas interface, that is dx cosine of theta star. Now in this case, the fluid does not impregnate the entire surface, but it leaves some trapped air in between. Now as a result, the change in the energy is associated when we move by distance dx. The change in the energy is given by we'll call it as DEC to represent the subscript C indicates that we're looking at the Casey state. Now we have the islands here, so phi s dx is the effective area of only the islands. So that's basically the gamma SL minus gamma S. But between the islands, we also have air pockets where we have an interface between the air and the liquid. Therefore, we also have to take into account that there is an area fraction of the air pockets with an area of 1 minus phi s dx times the respective surface energy, which is gamma, and finally the contribution from the interface. And if we set dE, if we set this quantity dEc by dx, if we set it to 0, we simply get minus 1, or rather we get cosine of theta star will simply be minus 1 plus phi s cosine of theta y. That's basically my Casey-Baxter relation. Compare this to what we have got here. The only these are identical expressions that I've put in this box, right? Now we can actually make some special cases here. As phi s goes to 0, which means that the area of the pillars, phi s is basically the area of the pillars. If they basically go to 0, then you have cosine of theta star, meaning that when the pillar density goes to 0, cosine of theta star goes to minus 1, and this means that theta star goes to pi. So this is a case which you observe for many hydrophobic surfaces, including the lotus effect, where the effective contact angle almost appears to be it appears like a super hydrophobic vase, where the contact angle often exceeds 150 degrees to 160 degrees. This is the kind of state that we observe when the area of the pillars basically shrinks. Now, let's look at the crossover between these states. Transition between Wenzel and Casey. Let's look at the transition between these states. Now, there are a couple of possibilities. One is if DEW becomes larger than DEC, this means that what is the expression for DEW? The expression for DEW was R times gamma SL minus gamma S of dx plus gamma times cosine of theta star dx. When this becomes larger than phi s, I'm writing now for the Cassie state. When this happens, it means that the Wenzel state has more energy than Cassie state. So the system will try to move towards the Cassie state if this condition, if this is the situation where DEW becomes larger than DEC. Let's look at some of the terms which get cancelled out. Clearly, this last term does not matter because you're not changing the area on the fluid liquid gas interface, and we can also cancel out dx on all sides, and we can do some rearrangement, and what we get now is minus r cosine of theta y plus cosine of theta star becomes larger than minus phi s theta y plus 1 minus phi s plus cosine of theta star, right? So now notice again that cosine of theta star will also get cancelled, and now we have a relationship between, an inequality between the roughness elements, roughness parameters, that is r and phi s, and the Young's contact angle phi y, theta y, and therefore we now have cosine of theta y will be less than minus 1 plus phi s by r minus phi s. Let's call this as cosine of theta c. So theta c is like it's a transition parameter, transition value, so, or a critical value. So when DEW becomes larger than DEC, one expects Cassie state to appear when cosine of theta y is less than cosine of theta c, or now let's look at the other case, which is called spontaneous waking. Now in this case, let's consider a situation where I have a roughness surface so we are looking at a case where is it possible to have spontaneous wetting. Now what does spontaneous wetting means? So let's first write down the energy for such a surface. Like if you were to pour liquid onto a surface, it would immediately spread on the surface. Now if this happens, then the entire surface is covered by liquid, and what tends to happen is the change in the energy for this configuration, when a fluid first traveled by a distance of dx, in this case it will be gamma SL minus gamma S of r minus phi s dx plus gamma times 1 minus phi s dx. So what really has happened is the entire surface has basically traveled all along the surface, and it's like basically a case where the apparent contact angle has basically gone to 0. And if we work out if we look at this case, then spontaneous spreading will happen spontaneous spreading or wetting of the surface will occur if this quantity d is less than 0. When d is less than 0, then the system is continuously able to reduce the energy by spreading on the surface. And now what we have is the Young's angle cosine of theta y, which is gamma s minus gamma sl by gamma. This is basically, it's coming from these two, this and this, the different surface energies. The cosine of this will turn out to be greater than 1 minus phi s by r minus phi s. So this is basically the case where we have spontaneous wetting if this condition is met. Now what one can do is, if we wish to make surfaces where liquid spontaneously wets the surface, then we have control on 3 parameters. 3 parameters to control, such that the above inequality is met. What are the 3 parameters? The first one, theta y, can be altered using surface treatments. So this comes under the domain of chemistry. You can change the chemical nature of the surface. Therefore, the equilibrium contact angle theta y can change. And now you can also engineer surfaces such that r and phi s can be controlled via geometry, meaning r and phi s are geometry parameters. So they can, if you can manufacture surfaces with a prescribed r and phi s, and if you can basically do chemical treatment on the surface, then you can always make a surface in such a way that it spontaneously wets the surface. Now, why would one want to make such a surface? You may want to have surfaces which spontaneously absorb and become wet, and they take away water. For example, if you're using a kind of a surface, let's say to clean a kitchen counter, you may want to have a surface which immediately, as soon as it comes in contact with the liquid, primarily water, the water immediately gets transferred onto the solid surface, because if it's basically effectively likes the surface so much. So therefore it is beneficial to also engineer surfaces, also make surfaces where water spontaneously spreads on the surface. Now finally, what we want to do is to come up with some kind of a transition diagram that we've seen. So we have actually seen 2 results. If cosine of theta y exceeds this quantity, 1 minus phi s by r minus phi s, then you have spontaneous wetting. And then if cosine of theta y is less than minus 1 plus phi s divided by r minus phi s, then the Cassie state is preferred. So now we can actually write down some kind of a simple transition between these 2 regions. So if I make a small table of Cassie, Baxter state and Wenzel state, So let's write down what we saw. In the Cassie-Baxter state, cosine of theta star, let's call it as Cassie-Baxter. What was the expression that we had for cosine of Cassie-Baxter? We had minus 1 plus phi s into cos theta y plus 1. So let's write that down. It is minus 1 plus phi s into cos of theta y plus 1. And what was the equivalent in the Wenzel state? Let's call it as W. And in the Wenzel state, we simply had R times cosine of theta y. Now, what about the validity of the Cassie-Baxter state? We find that Cassie-Baxter state is valid when this inequality is satisfied. Cosine of theta star, Cassie-Baxter, sorry, not the Cassie-Baxter, cosine of theta star times the contact angle of this equivalent smooth solid surface is less than minus 1 plus phi s divided by r minus phi s. And in the case of Wenzel state, we have minus 1 plus phi s divided by r minus phi s. If it's less than cosine of theta y is less than 1 minus phi s by r minus phi s, then you actually have the Wenzel state. And once you exceed, if cosine of theta y exceeds this quantity, maybe we can also do this. If cosine of theta y exceeds 1 minus phi s by r minus phi s, then you have spontaneous wetting that occurs. So we basically looked at some rough transition between these various kinds of wetting regimes that are possible. I want to do one small extension of this analysis, and this is something that I'd like all of you to attempt this as an assignment for the course. We can also have an alternate derivation. Alternative approach to Cassie, Wenzel, and Young's equations. Okay. The idea of this alternate approach is something that we have already done for the Young's equation. Let's consider a droplet. It's a spherical cap. So they are in the spherical cap approximation. No gravity. At the very least, the droplet is so small that gravity is not important. And if we say that there is a droplet which is basically making a radius of r, then we can write down the volume as pi by 3 r cube into 1 minus cos theta whole square into 2 plus cos theta. And we can also write down the surface area as two pi r square into 1 minus cos theta. That's what we have. So now we have the radius of the droplet given as r. We can also write down some kind of a wetting radius, which is, let's say, as a, and this a is r sine theta. And so now we can write down an energy functional for this. The energy functional essentially would be, let's say you have an energy functional J. This would be gamma times S. Then we have the surface area of the solid on the solid, and this quantity essentially would be gamma s minus, instead of writing it like this, we'll write it as pi r square, a parameter beta times a sine square of theta. The idea of this parameter beta is that this parameter essentially can be applied for different settings. Now, beta for a flat interface, beta is simply gamma s minus gamma sl. And in the case of the CASI, let's say in the case of, well, we can take the Wenzel state. Now, in the case of Wenzel state, this is for the Young's, this gives me the Young's equation. If I apply this beta to be R times gamma s minus gamma sl, then we get the Wenzel model. And we can do something similar for the Casey-Baxter state, where now beta will involve the roughness elements, or beta will involve the chemical heterogeneities. Now, once we do this, we can do an energy minimization and get the same result what we had done. This is a simplistic model of, this is a more like an exact model of the problem, where we don't really are not considered about the nitty-gritties of the position of the contact line and how it's interacting with the surface. All of this is modeled with this parameter beta. So with this, I conclude the discussion on wetting on rough surfaces. Let me quickly recap what we have seen in this topic. We've looked at cases where we have a rough surface, and the rough surface was modeled with idealized textured surfaces. We've looked at the cases, 3 different cases. We have the Casey-Baxter state, where we have chemical heterogeneities. We have looked at another Casey-Baxter state where we have air pockets entrapped between the droplet and the surface. And then we also had the Wenzel state, where the liquid penetrates into the solid surface. There are more cases that one can always look at, which is beyond the scope of, it will take us too much of time and effort to go through all the possibilities. For example, there's something called a Casey impregnation state, which is a combination of spontaneous wetting and where the liquid basically wets the air pockets, but at the same time, it also the liquid also penetrates into the grooves ahead of the contact line. This is different from the Wenzel state. Therefore, an additional excess surface energy is also created when the droplet basically sits on such a surface. But it's something that we cannot look at all the possible cases. We could also have surfaces which are curved. We could have a combination of chemical heterogeneities and rough surfaces. All of those are possible. But I hope this discussion and the way we've analyzed this has motivated some of you to delve deeper into this topic. This is an active area of research where engineers are now able to make surfaces with precise control on the roughness parameters, and a variety of novel properties can be created. Surfaces which are self-cleaning can be created. I started the lecture, I started the discussion by mentioning the word biomimicry. So engineers are able to look at surfaces in the natural setting. For example, it could be the feathers of birds, or the wings of insects, or the leaves of plants, and they're able to make surfaces with similar properties. As I already said, as an engineer, one can play around with 3 primary parameters. One is the Young's angle for an idealized smooth surface. Then you can play around with two roughness parameters. One is this parameter R, which was the ratio of the roughness, the total surface area of the rough surface to the surface area of the projected surface, and the parameter phi s, which was basically the ratio of the area of all the islands, where if the droplet is sitting on the air pockets, the area of those islands to the projected area. So the roughness parameters, one can play around with careful engineering to get roughness elements the way they want. And then the next step would be to do some chemical treatment to change the contact angle theta y. And then one can try and make surfaces with specific properties. So with this, I will end the discussion on wetting on textured and rough surfaces. Now, I also at the beginning also mentioned about this case of a droplet that is sitting on a tilted plate with two different angles. This is also a case where the angle is different from the Young's angle. This is comes under the topic of contact angle hysteresis. That is something that we'll be looking at later in the course as well. I'll see you around in the next lecture. Thank you.